Now I have the pleasure of introducing our next speaker, Dr. Doug Braun. He's a research scientist with DFO's Freshwater Ecosystems section and an adjunct professor with Simon Fraser University's Department of Resource Environmental Management. Doug's research focuses on environmental influences on salmon at the individual and population level, salmon ecology, and environmental monitoring. Doug will be giving us an overview of his team's North Thompson Salmon Ecosystem Research Program. Over to you, please.
Thanks, Chrissy. Good morning, everyone. It's a pleasure to be here to talk to you about some of the work I'm doing and hopefully can provide some insights into how this relates to restoration work and monitoring. So I'm going to talk to you today about the North Thompson Salmon Ecosystem Research Program that myself and a team of researchers have started working on. And so this work is primarily conducted by myself, Emma Hodgson, and Sean Naiman, who are all research scientists in the freshwater ecosystem section at DFO. We all have various interests from cumulative effects to land use impacts and fish habitat relationships. We also, just to acknowledge, we have a team of biologists and students that really help do a lot of the work that I'm going to talk to you about today. And so just to acknowledge those folks. And so the research themes for our work really is to identify important juvenile salmon habitat, to understand how different freshwater habitats contribute to salmon productivity, and to better understand how human activities impact salmon and their habitats. And so really guiding a lot of this research early on is this paper by Tim Beachy and company, where they looked at estimating coho salmon rearing habitat and smolt production losses in a large river basin, and applied those insights to the implications for habitat restoration. And so they argue that a watershed perspective is required to truly understand and plan out restoration activities, so you don't have a mismatch between the losses of habitat due to land use and the potential gains from restoration. And so this was kind of a foundational piece in our thinking and developing this program. And so here we're really trying to take a watershed approach to habitat science. And our rationale for picking the North Thompson, which is on the traditional territory of the Secwepemc First Nations, is because there are many populations of salmon, in particular interior Fraser coho, that have declined over recent decades, and numerous reports that identify and describe these declines. In these reports, they also have threat assessments that imply fresh water is a key factor in the decline. And many knowledge gaps have been identified for interior Fraser or interior coho salmon. And I think you could probably apply this to any large watershed throughout British Columbia, this same kind of criteria. So there are a few other reasons why we decided to dive into the North Thompson as kind of a focus of our program. One, an important reason is the gradient and land use in this region is quite broad. So we actually could find systems where there is very little forest harvest, for example. So some of the watersheds only have around 1% of the area that's been harvested in the past 60 years. And this is particularly challenging to find, as most of you will know, throughout British Columbia. And they also have sites and watersheds where up to 60% of the area has been harvested in the past year. So a pretty dramatic gradient in land use. There's also a gradient in climate, which poses some really interesting questions. So down in the lower part of the watershed in Kamloops, we're in pretty much a desert, all the way up to the headwaters of the North Thompson, where we're in a temperate rainforest climate. And there's also really lots of replicates. So we have a lot of space, a lot of individual streams that can serve as replicates, which give us power when we're diving into the ecology and land use impacts of the system. And the goals of this program really are to undertake most projects at the watershed scale. So that means that we're trying to, for any given project, have have the project extend where sites extend across the entire watershed, or go from basically Kamloops to the upper North Thompson. And when necessary, we conduct intensive studies to understand mechanism and process. And so sometimes not everything's all worked out, and we need to dig into certain processes to really understand what's going on. And as we do this, we build layers of information, and these are usually models which can be visualized through maps. And together, these layers of information will be stitched together to kind of give this watershed perspective of salmon and their habitats. This is just a schematic of kind of the different attributes that we're focusing in on. So at the base level, we're trying to understand land use and landscape attributes. We then kind of move up into understanding environmental conditions and physical habitat through basic monitoring. And then as we get more research focused, we dive into some ecosystem processes, more targeted fish enumeration, and then trying to understand general fish ecology, such as growth and habitat use. And so as we build these different layers of information, we can kind of pull them together to try and understand or try and produce a bunch of research outputs, primarily focusing on habitat productivity relationships, indicator development and validation, land use impacts and cumulative effects, and management prioritization and evaluation. And this just gives an impression of the number of sites or the scale at which we're looking at these different ecological components. And so, we have up to 35 sites for looking at physical, environmental, and spatial data. And as we move up into more intensively studied areas, we tend to reduce the number of sites. And so increasing the intensity of our investigations, but reducing the number of sites. And this just shows some of the different things that we're monitoring and researching in the watershed. And it goes from the left side of your screen from the more extensive, broader scale investigations to the more intensive and detailed studies on the right of your screen. So environmental conditions such as temperature, flow, dissolved oxygen, physical in-stream habitat, and landscape features that affect flooding. Moving into ecosystem components where we're looking at water chemistry, nutrients, invertebrate abundance, stable isotope, and fish diets. And then when we get into fish, we're understanding abundances through mark recapture, looking at movement, size and age composition, as well as physiology that describes the energetics of fish in the system. So another way to think about how these different kind of layers of information or intensities of investigation can feed into better understanding things like restoration or management actions is through the idea that we can understand process, and together with pattern, we can predict or better plan action in a watershed. And so the processes are kind of the why and the hows, so mechanisms and processes, more intensive studies, and usually a focal set of study sites. The pattern is where we move to the where and the when of things. This is where the level of indicators or surrogates kind of sit and really focus on more extensive studies, so more sites that span the watershed. And with those together, we can think about how we would predict the future state of habitat or populations, the outcomes of management actions, and outcomes of environmental change. And so for the first kind of few years of our work from 2019 and still ongoing, we're focusing on this process and pattern and really trying to, again, develop those layers of information. And the future work will entail combining that to think about how we can predict the future state of the habitat, as well as think about planning for different management actions, like things like restoration throughout the watershed. And so for the next bit of my talk, I'm going to dive into a couple of examples of work that we're currently doing that kind of hit these different research themes. And so going back to the idea with that the Tim Beachy paper, looking at restoration planning from a watershed perspective, the components that they really described in that paper were understanding where fish were, how the different habitats contributed to the productivity of the watershed, and also where the impacts were and the land use activities that cause those impacts. And so those are kind of really follow those three research themes that we have laid out. So for the first project, we're really interested in identifying important juvenile salmon habitat. And so mostly we think of juvenile salmon rearing in streams or in big lake systems if they're sockeye, but really juvenile salmon are throughout the watershed. And so we're interested in where these fish are other than the spawning tributaries. And so we have projects that are focusing on habitat use in wetlands, as well as the main stem North Thompson. And really we want to understand not just where they are, but when they're there. So what are the seasonal dynamics of habitat use? And so on the right-hand side of your frame, we have an overview picture of a wetland system that we're currently working in. And so I'm going to focus on the wetland component of this for the rest of, as an example. And so here we're looking at juvenile coho salmon use of wetland habitats. There's 3 focal wetlands that we're studying. We have monthly fish sampling from April to October. We're looking at coho growth, age composition, and density. And we also want to understand what's going on from the environmental conditions perspective. So we have continuous loggers for temperature, dissolved oxygen, and water level that gives us indication of how connected the wetlands are to the main stem North Thompson. And so looking at our fish surveys, this is for one of our sites. You can see seasonal change in the abundance of fish. So fish tend to move in the spring during freshet. And so you can see on the x-axis of this figure, we have the months of the year from 2021, starting in May, through to 2022 in October. And so we see an increase during freshet, which is those first 3 months, to a peak abundance in July. And then the abundance of juveniles tends to decrease into the fall. Over the winter, we do not survey. A lot of these systems are iced over, but they're also disconnected from the system. So what we find in April is usually a result of overwinter survival in these systems. So there's a couple of key things to take away from this plot. One is that there's year-round use of wetland habitats. And so this is different than what we traditionally see in the coastal wetland systems, where fish are coming in the fall or in the winter, using them as flood refugia. Here, they're coming in the spring and using the entire system throughout the year. And the other key piece to take away from this is that there's large variation in abundance. And so for this particular wetland habitat that we're surveying, you can see that there's estimated abundances for a small reach up to 10,000 juvenile coho salmon. And in the following year, in the exact same reach, we had in the order of 100 fish estimated. And so we can look at the different environmental conditions to try and understand how what might be driving these differences in abundance. And so we look at the thermograph for the 2 years of the system. It looks pretty typical, nothing dramatic. The blue lines are where the system are connected with the North Thompson. And so you can see during freshet, the influx of cold water from the North Thompson in the beginning of the 2 hydrographs. So temperatures seem quite reasonable, maybe a bit high in the summer, but really doesn't affect how fish are coming in. When we look at dissolved oxygen, we can see that there's a lot of variability, not only throughout the year, but also in key times when these fish are migrating into these systems. And so in the first year in 2021, when we sampled, there was a couple of punctuated flood events from the North Thompson that provided fish with access, but also had some real changes in dissolved oxygen. And so we only saw that a couple times in the 2021 year. In the following year, we see a long sustained freshet and flood event, and it really drove very different dynamics in the dissolved oxygen, which we think led to led to fish not coming in the same numbers that were present in the year before. And so some summaries and connections to restoration here. Juvenile coho salmon use wetlands year-round. The timing of immigration and emigration are similar among all the wetland habitats that we're looking at. So there are some consistencies and generalities that we can apply to these different systems. Juvenile coho salmon productivity is highly variable. So within and among habitats, we saw incredible variation in the number of fish that were in these systems. And it appears that there's complex flood dynamics that are affecting the environmental conditions that kind of set up that immigration into these systems early on in the year. And so what we can learn from this is when we're thinking about restoration or, for example, reconnecting some of these habitats, it matters when you sample. And so thinking about how you would actually monitor the function of these systems, the spring conditions might be really important for determining occupancy. And in terms of thinking about sampling and understanding, how effective some of these restoration projects might be, there's massive variability in not only the environmental conditions, but also in the total abundance of fish in these habitats. And so monitoring for wetland function for juvenile salmon is quite complex. And so these spring environmental conditions are important, and understanding what the targets are, developing targets for the environmental conditions are probably really important. And not all habitats appear to be viable each year, or at least strong producers. And so this is important because you could, for example, reconnect a habitat and not actually see the production in a fish that you might expect. And these tend to be a bit different than, your classic stream restoration project, where the conditions from year to year and within years are, especially when you think about something like temperature or dissolved oxygen levels, are probably pretty stable. And so the work that we're doing here can, I think, provide targets for wetland habitats in terms of the environmental conditions we should expect and that could be used by fish, juvenile coho salmon, and their dynamics in those different environmental conditions. And then also, what are the expectations of juvenile coho density for these different systems? So going back to this schematic, just to place the work in some context, we can understand these processes of how these fish immigrate into these systems, how complex the flood dynamics appear to be that influence immigration, and how the high interannual variation abundance is likely due to dynamic environmental conditions. And if we take this understanding of process, we can then survey other wetlands across the entire watershed. So where are the wetlands that might be usable for juvenile coho salmon, and when are they available? And putting those pieces together, we can think about how we would prioritize sites for increasing connectivity between the wetlands and the main stem, North Thompson, prioritize sites that are most likely to be used by juvenile coho salmon, and protects the sites that are stable and productive. So those are really the next steps for this piece of work. So moving into our third piece, our third research theme, better understanding how human activities impact salmon and their habitats. And so this kind of shift gears from understanding more general ecology to really what are the impacts of forest harvest on juvenile salmon habitat. So placed in the same watershed in the North Thompson, here we're taking things like the mechanism of impact to watershed processes and assuming that they're largely understood. And so the caveat here is that the research that's gone on to develop those mechanisms of impact are really focused on small coastal streams. And given that we know largely what the mechanism impacts are there indicators of forest harvest impacts? Has function been impacted? And so can we measure these kind of broader or more functional indicators to try and understand the impacts across a broader scale? So if we know the process, can we just monitor the pattern? And so again, going back to the same idea here, we have the processes that are reasonably understood. We have patterns where we can look at the extent of where forest harvest has occurred, where riparian habitats have been harvested, and what's the frequency of disturbance. So what are the timescales of that? And then from there, we can hopefully try and predict impacts to the watersheds and identify where and how to restore habitats if we know the mechanisms. And so we set out to sample 28 streams for various physical habitat features. So all these different components of the ecosystem here. And the map on the right just shows the distribution of our study sites throughout the North Thompson. And so those are all small tributaries that connect with the main stem North Thompson. And this is just a schematic kind of providing a bit more of a visual of how we go about measuring these different components of the stream, which I'm sure most of you are familiar with. And so we measured a kind of the state of the habitat, and we needed to then understand what were the forestry activities over the past 60 years. So we, for these watersheds, looked at the upstream percent riparian area harvested, the percent of the watershed clear cut, and the road density and stream crossings upstream of our study reaches. And using that information, we built models relating habitat characteristics to forestry activities. And importantly, we accounted for watershed characteristics and reach gradient. So it's the gradient of the reach that we sampled. So the general model looks like something like we have our habitat variables, which are a function of forestry activities and watershed characteristics. And so just to give an insight into what the forest harvest looks like across our sites, we have this really nice gradient of forest harvest across our 28 sites, ranging, like I said in the introduction of the talk, from 1% to upwards of 59% harvested over the past 60 years. So when we put the data together, when we looked at physical habitat, the one thing that came through was that gradient was a strong predictor of many of the habitat features throughout the watershed that we measured, or throughout our reach. And so those are kind of static indicators or static variables of habitat state. Another component that was really important that we looked at was water temperature, which tends to be a bit more dynamic and potentially responsive to forest harvest. And so what we found here was the proportion of riparian habitat harvested strongly influenced the maximum water temperature in these sites, such that streams with 35% riparian harvest were on average 3.7 degrees warmer than streams with only 5% riparian harvest. And so you can see on this figure, you have percent harvested on your x-axis and the average daily maximum temperature on our y. And the purple and the orange indicate, the purple indicates the proportion of the area that was riparian area that was harvested, and the orange is the total watershed upstream that was clear cut, total proportion of the watershed upstream that was clear cut. And if we look across various temperature metrics, we see the same pattern where there was a stronger relationship between the riparian habitat that was harvested versus the entire watershed that was clear cut, which suggests these are obviously important habitats for regulating temperatures in streams, which is not really surprising. I think what what came from this study was that when we looked at the watershed characteristics that describe most of the variation in watershed characteristics describe most of the variation in physical habitat. So REACH explained most of the variation in these physical variables that we measured, and really this suggests that there's a lot of variation across all these sites, and they're really determining in a lot, mainly what the physical habitat looks like. The proportion of the riparian area harvested had a strong influence on water temperature. This is obviously likely due to solar increases in solar radiation, and it suggests that riparian harvest could be an indicator of temperature impacts on freshwater salmon habitat. So thinking about how this relates back to restoration, watersheds vary in space and time. And so this really needs to be accounted for with watershed characteristics. So what happens in one watershed is likely very different than what happens in another watershed. And so thinking about restoration projects and how they're monitored, this really needs to, these watershed characteristics or this watershed context needs to be accounted for. So that we're not missing pieces of how these restoration projects are, how effective they are. And the other piece that's really important is that forestry impacts can be episodic and transient or persistent. And so the dynamics of how forestry might impact a watershed range greatly depending on the mechanism. And so if we think about episodic or transient kind of impacts, we can think about sediment inputs or bank failure or landslides. So these are things that could happen at different times, and it might be years before these impacts actually come about. And so really that suggests that, just because you measure a habitat and the physical habitat, it might not be indicating of what's to come in the future, given that some of these impacts are episodic. As well, we look at something like riparian harvest and the revegetation process. And so this persists typically between 1 and 30 years. And so this is where temperature is a reasonable metric that shows a relationship, because this riparian harvest has a persistent effect. And so we'd expect that we would see these a predictable change in temperature across this time scale, whereas other things like sediment inputs or large woody debris loss might be episodic and might not be realized for decades to come. And so the key take home here is that these temporal scales of forest harvest impacts can vary from days to over 100 years. And so thinking about how this might, if we have restoration projects that are targeted towards restoring habitat affected by forest harvest, we really need to think about these timescales. So restoration plans should really consider the temporal and spatial scale of the impact. Large channel forming disturbances that are episodic or transient may compromise the effectiveness of restoration efforts. And monitoring these projects that are in systems where we have these long-term and episodic impacts, monitoring something like function in and around the restoration project might not be a good indication of future function. And really, we want these projects to continue on and provide a benefit for decades, if not centuries. And so just going back to this schematic here, I hope that I've kind of provided some insight as to how understanding these processes and merging them with pattern can help us think more about how we predict to understand the future, and as well how we plan our actions to restore habitats. With that, thank you.
All right, thanks, Doug. Appreciate that talk. I have a quick question for you, and we can get more into this a little later when we get to panel. But I'm not a scientist, I work in the world of fish habitat. I've been a regulator. I've been a supporter of restoration, other things like that, planning. One of the things that part of me was thinking when you were talking, it's like, all right, I get it. Like, but this is big science. So is it, for a guy like me, do I just sit there and wait for it? Like, I guess Doug and a team of people have to go and study something, and I'll have to wait a decade or two for you to come back and say, hey, here's what you can do. Or is there a takeaway in here that people from smaller organizations, groups that are doing localized restoration, who can't do the big science, but can appreciate what you're talking about? Is there a takeaway message for those groups that are working more locally, maybe on smaller scale things?
Yeah, for sure. And so I think, I didn't want to suggest that we need to wait decades for the science to come out on this, but more, I think, just thinking about when you're for these individual projects, when you're in a system, thinking about the processes, thinking about the fish ecology might provide some context for the different decisions you make when implementing a restoration project or monitoring it. And so, I think the takeaways are try and understand the process or think through the processes that are going on that you're trying to restore essentially, and how that might play out across the landscape, or how the context of your specific watershed might differ from others. So I think that would be the more localized advice.
Well, awesome. Well, that's a great wrap, and I think looking at some of the questions that are in the Slido, we'll probably get into that thread a little more when we come to panel. So, Doug, thanks for that talk.